Well, thank you so much for coming, and it's a real privilege to be hosted here, and I've just had such a great time here in Bengaluru. The mediators have been explaining so much about carbon that I didn't even know, so it's been a great educational opportunity for me to also hear about the history of carbon in India and understand the complexities but also the future of this element here in India. Today I'm going to talk about the atomic view of a battery. But as I was going through this exhibition, there were a lot of questions that came up from different mediators and people, so I'm going to try and fold those in as well. But before doing that, I want to highlight all of the amazing people I get to work with. And a lot of the work I'm going to be showing here are from my colleagues. So I work very closely with Associate Professor Nigel Marks, and we both co-lead the Curtin Carbon Group, and that's in Western Australia at Curtin University. And we've got a great group of PhD students, masters, honours, and undergraduate students that make all this work possible. So just really want to highlight them today, and also, of course, all of the funders. And I also acknowledge that a lot of this work was done in lands in Australia that originally belonged to the Noongar Nation. And so just wanted to respect them and acknowledge them in this work as well. And the reason I'm here is because of an exhibition called Carbon Nanoverse, which is currently across the hall. And it's a virtual reality experience where you can step inside of a battery, become the scale of an atom, and move around a battery as if you are an atom, or maybe a lithium atom that is going inside of a battery, which we'll talk about a lot. And this work came about from molecular models that, or atomistic models that have been produced in the group for the last decade, but also in collaboration with Dr. Andrea Rassel, on a creative fellowship, we were able to produce this work. I should also mention Callum Wood, who was a third-year student, but is now a PhD student with us, and he actually wrote the Unity code that made that exhibition possible. And it's been wonderful to see people, at least online, seeing lots of different groups engaging with the exhibition. Here in Bengaluru, and school groups and politicians, and all of them having a different perspective of carbon, maybe less about emissions and more about our carbon future, which I'll touch on. This here is a view inside of that, one of the models. So this is actually a model of charcoal, which is a way that we can actually sequester carbon. And you can actually zoom around with the joysticks and go wherever you want in the model. There are actually 1 million carbon atoms in these models, and they're some of the most complex structures that we know of in carbon material science. So I'm going a bit fast there. The other thing that I've really enjoyed is some of the exhibitions here, and I can't go through any of them in too much detail because there's not enough time. But something that had really caught my eye and my attention was an incredible exhibition about C.V. Raman and his contributions to science, to physics, but telling specifically the story of diamonds and his fascination with diamonds. And the exhibition actually starts off talking about the Kohinoor diamond, and C.V. Raman's referring to it as a sad story and wanting to have that diamond back. But then it goes into his fascination with the diamond atomic structure and the vibrations within that structure. And something that was just wonderful to see is this model here. So this is from the Raman Institute, from their museum, and this is C.V. Raman's model of diamond. And you can see it in the exhibition, and this is something that I'd never seen before, and it's such a wonderful thing that you could only get here. So what I wanted to do is, of course, you can have a look at it, but don't touch, but I actually created a model of that using more modern molecular modeling tool, so plastic, whereas this one's made out of wood and brass rods. So I'll pass that round so that you can actually have a look at the structure and kind of look at it and hold it, because these models were meant to be held. You can see C.V. Raman there actually holding it and looking down the planes and understanding the crystal structure. So I'll just pass that around for you to enjoy. There's also some great work on sort of some of the research that happened in India, and also just some amazingly beautiful exhibitions. So I really recommend having a look around and really enjoying this, the story of carbon told in so many different ways. When I think of different carbon materials, I think about the different atomic arrangement of those atoms. So we were just talking about diamond here, and you can see the diamond structure. The diamond structure, each carbon atom has 4 neighbours, and so it forms a little tripod, in a sense, and that's how it holds itself together and makes it the hardest material. Whereas graphite is made up of sheets of carbon atoms that are connected to 3 neighbours, and those sheets can slide past each other, making it one of the softest materials. On the other side of the scale, we have something that's completely amorphous, which means that there are no short-range or long-range order. So this is a material that you can make. It's called amorphous carbon, and that's actually used to coat tools. We have the facilities in the laboratory in Perth to do this using sputter coating. You can see there's no order. But one of the most complex areas of study is this disordered region, where you have some short-range order, but no long-range order like you have in a crystalline solid. And there's a lot of interest in these materials and how they can convert into more crystalline materials, which we'll go into. But I just thought I would start off with some nice molecular structures for you. So this talk has got 3 main contributions, or 3 main ideas. The first bit I added in because I had so many great questions from the mediators, people who are lawyers and scientists and activists, people that care about carbon, people that care about carbon as a significant problem, but also people that are seeing carbon as part of the solution. So I'm going to start off by talking about that. And then we're going to go inside of a battery using some 1950s 3D technology, these 3D glasses, which should be all on your seat. So that's fairly rudimentary. And then I'll talk about how we used virtual reality to make new discoveries in the formation mechanism of graphite. And then after this, there's actually an opportunity. I'll have the VR headset that you can go inside the structure of diamond. So that's something that you can't do in the headsets that are here. So I thought I would provide you that opportunity today as well. So let's talk about carbon as a problem. And I'm currently in Western Australia at Curtin University over here. And I wanted to kind of put us, we're across the Indian Ocean, but we're actually very close in a lot of ways. And one of those ways is the way in which electricity is produced. So in India, the predominant source of energy is coal, and it's the same in Australia. And there are also renewables that are coming online, but it's still a very fossil fuel dominated energy market, and that doesn't change for heating and other things. And we all know the problem. Carbon is going into the atmosphere. So I did my PhD on soot pollution reduction. Soot is black and it absorbs the heat from the sun and it heats up the atmosphere. That's fairly straightforward. Methane and carbon dioxide absorb the infrared light that the Earth gives off as it tries to cool down. And that basically turns that light, the infrared light, into heat. And so these 3 different carbon in the atmosphere are leading to increase in the temperature. And this is a significant problem for us all to deal with. And this is where we're headed. So by 2070, Australia and India and the rest of the world is anticipated to be 100% renewable energy, not producing carbon dioxide. But when you look inside of the renewable energy, you'd be surprised to find a lot of carbon, okay? So inside most fuel cells, there are carbon plates that transfer the electricity and allow for the hydrogen to be converted into water. Inside all of the hydrogen fuel tanks, it's carbon fiber. Inside all the brake pads, which we still need, it's a lot of carbon. Inside the supercapacitors, there's carbon, as activated carbon. And what we'll talk about a lot today is lithium-ion batteries, which must have graphite to function. And so a lot of the work that we do in the Curtin Carbon Group is focused on the fundamental science, but applying that to enabling our green technology. So instead of burning carbon, putting it into the atmosphere, how can we embed it into the green technology that we need in order to decarbonize? So using carbon to decarbonize. So the batteries, supercapacitors, fuel cells, we're also looking at taking the carbon out of fossil fuels and making black pigments like carbon black. And then also using carbon to protect materials from hydrogen. And something that, that we've been working on with an Indian company, Himadri, which is actually one of the only companies in the world, I think it is the only company in the world that's able to turn coal into a liquid that can turn into graphite. And I'll talk about why that's very unique technology, and that's an innovation that happened here in India. And the spodumene, which is the mineral reserve of lithium in Australia, is now the biggest producer. We're now the biggest producer of lithium in the world. That's why I'm in Western Australia. Lots of solar, lots of lithium, lots of nickel, lots of graphite, lots of minerals that are needed to make batteries. And of course, these are going to go into electric vehicles, but also grid scale storage. And I had a discussion with a few people saying that they were concerned about batteries. They thought, well, aren't they just going to cause a whole bunch of new damage to the environment because of the mining and because of the emissions associated with producing those materials? So that is obviously a very important question, and it's a question that the scientific community has spent a lot of time trying to answer. And so there's a variety of different studies looking at the greenhouse gas emissions over the entire lifespan of a vehicle, and they find that in different places, depending on the energy mix, so how much CO2 is emitted per kilowatt hour of energy, how much better is an electric car versus a gasoline car. And you can see that there's a significant improvement over the lifespan of that vehicle. And as our grids become more green, so this is going from 2021 to 2030, as our grids get cleaner, those cars are going to have an even better reduction in our CO2 emissions. And I'm more than happy to chat about the ways in which we can make the minerals and prepare those minerals with less damage to the environment. The other thing I just wanted to talk about when we talk about carbon is it can be anxiety-inducing. I don't know about you, but when I try to think about these problems, it can become very overwhelming very quickly because in a sense, it's all of our problem, but in another sense, it's not our fault. But it is also sort of our fault. And it's a very difficult thing to think about. So what I want you to think about here is turning footprints into handprints. So most of us think about our carbon footprint a lot, or at least I do. And our carbon footprint is a problem, and we can tread more lightly on the soil around us, and we can produce less carbon. But really, the only way for us to stop having footprints altogether is to not be here. And I think a lot of people are in a very sad place, and that is somehow how they can get to very depressed places. But what I want to remind you of is that we have hands as well, and these hands are able to offset the footprints. And so if you reframe it as, what can I do with my hands in order to make sure that I offset my own footprints, but the footprints of others as well, can be a very sort of enabling thought. Here's my sort of tips that I give to students when I talk about climate change. The first thing I recommend is trying to imagine a future where climate change is under control. Climate is changing, it will continue to change. But try and think of a future where it hasn't changed beyond tipping points. And there's a very good documentary called 2040 that sort of explores that. The second thing I recommend you do is think about using whatever skills, knowledge, and gifts you have to use your hands to make the situation better. If you're a lawyer, use those tools. If you are very good on the land, use that skill that you have. If you're very good on computers, use that and try to reduce emissions. Reduce as much as you can, consider offsetting, and then thinking about how our handprint can offset our footprint. And then I recommend talking to others about it. So there's quite a nice talk from Catherine Hayhoe, who's a climate scientist, who talks about the most important thing we can do about climate change is talk about it. When we stop talking about it, we just ignore it, and that's not a good solution. And then if you have skeptics in your life, I recommend, I have a TEDx talk about talking to climate skeptics. So I recommend that because there are some really good discussions, and no one is beyond a good conversation and encouragement to see the world as it is. And the last thing I just want to say is be kind to yourself and others, and seek help when you're feeling overwhelmed. I have this slide on my website if you want to have a look at it, but just want to help you out because, you know, it's tough stuff. So we're going to now look at a lithium-ion battery. Now, the reason I want to do this is it helps you to understand a battery, and it's not sort of this hidden, invisible thing with some random chemistry going inside. It's actually fairly straightforward, and if you have that atomic perspective, it just makes me want to have more batteries in my life because they're so cool. And then I'm going to talk about how I've used my sort of skills and the skills of those around me, and we've together been able to make some leeway on how to make graphite for batteries with less emissions. So let's start off with a battery. So a battery is actually made up of many, many cells, and these cells are usually where all the chemistry happens, and you can extract the electricity or put the electricity into these cells. There's also cooling loops as well that are usually put inside of electric vehicles. So let's have a look inside. So this here is a CT scan from inside of a battery. It's almost as if you've got a dental exam, okay, but for a battery. And you can see it's made up of all these layers. Now, those layers come about because all the material is put in a very fine paste, and then it's put in a roll, so it's rolled up, okay? And that just means you have lots of surface area for the chemistry to happen. Now, if we zoom in using an X-ray CT scan, you can see that there's a few things going on here. There's some sort of material here that's flake-like. There's some other material here that sort of looks like little blobs, and then there's a separator here. Just to give you a sense of scale, this is the width of your hair, okay, for perspective. So the whole chemistry of a battery is happening in the width of your hair. It's a very, very small distance, okay? And we're going to get even smaller. So this is a beautiful schematic that was done by the YouTube channel, The Limiting Factor. It shows you this is the flake-like material here, copper foil. It's got a plastic separator here, and then it's got some other material over here, which is the metal oxide, and then aluminium foil. And this here is what's repeated. So you end up having some of this material here, and then you've got the separator, and then you'll have this material over here. So it sort of oscillates between the two. And this is a scanning electron micrograph of that. You can see the plastic separator there. you can see the graphite over here, and you can see this material here. Now, on this side, there's actually some really beautiful oxides. So you have mainly cobalt oxide, and then more recently there's this lithium iron phosphate that's been used. But the cobalt oxide is actually a beautiful glaze. And I was actually talking to a potter who is a ceramics expert, talking about how it's quite expensive to buy cobalt oxide glaze now because of the use in lithium-ion batteries. So this beautiful blue compound here is on one side of the battery. And this compound was found by different scientists as being a good place for lithium to go when the battery is discharged. So if you could put on your glasses and put the red on the left side and the blue on the right side, you should be able to see it in 3D. Thumbs up if you see 3D. Wonderful. Okay, so we're all going to look cool together, so I'm keeping these on. So we've got lithium ions here, and then we've got cobalt, nickel or manganese, and oxygen. Now, I've put them as spheres. They're actually a bit bigger, but it's a bit hard to see if I make the spheres any larger. I'm going to put bonds between the metal and the oxygen, because those form covalent bonds. And then I'm going to replace this with boxes, because that's going to make things even easier. So these boxes, these sort of prisms, are the metal oxide. And now we're going to zoom through that. And what you can see is that there's actually a layer below and there's a layer above, and the lithium is sandwiched between the layers. Now the lithium in this case is lithium plus, and we're going to go up and through the layers. Sorry, I'm not a very good driver, so you're going to hit it. Sorry about that. I do get my bearings eventually. It's a little hard when you don't have the VR headset to know how to drive around, but you can see here that you've got layers of metal oxide and layers of, all right, sorry about that. Not very good driving. So when you charge your battery, the lithium goes from in between those metal oxide layers to the other side of the battery. What's important here is the lithium needs to go through the liquid, but the electrons cannot. So there's actually a barrier, a plastic barrier, that stops the lithium, stops the electrons from making electrical connection between the two. If there is electrical connection, there is a short across the battery and you create a lot of energy quickly, and this is a failure mode of the battery. So that is what happens when you charge your battery. This here is a simulation that was done, and the reference is down here. These are the molecules that are in the liquid that hold onto the lithium ion. So you can see these molecules here, and they pass the lithium ion from one molecule to the next, allowing it to travel through the electrolyte solution, which is just a salty solution. Now, the Nobel Prize was given to John Goodenough and Stanley Whittingham for developing the metal sulfides, metal oxides that enable lithium to be stored when it's discharged. But their initial batteries had metal, lithium metal on the other side. Now, these batteries were not very good because they would explode regularly. And so what happened next in the 90s was, so the way that they would fail is that the metallic lithium you would grow these little whiskers called dendrites, and these whiskers would puncture the plastic separator and would short the battery, and then that would be the failure of the battery. They would, explode violently. This here is actually a video taken by Akira Yoshino of a lithium battery with a metallic lithium anode. Not good. Fire. Much damage. Okay. So what Akira Yoshino did, who was an industrial chemist in Japan, is he realized that he could put carbon into the battery. Initially, it wasn't graphite. It was a type of semi-disordered carbon, but it was a carbon that was layered. And eventually, at the end of the 90s, the graphite replaced that. And so on the other side of the battery, he added carbon, or graphite in this case. And this made the battery safe. So this is the video he showed at his Nobel Prize lecture that convinced Sony to make lithium-ion batteries. So this is the smash test with carbon in it. Beautiful. No fire. It probably would have heated up a little bit over time, but that's a good result. And this is what convinced Sony and others to manufacture the lithium-ion battery. Now imagine if that had exploded. We wouldn't be where we are today. At least it wouldn't have moved at the speed that it did. And that's only a few things that Akira did. He did a lot more than that, but I can't go into it now. So let's zoom inside of that graphite, and let's have a look at what the lithium's up to. So if you put on those glasses again, you can see the lithium metal and the carbon. Now I'm going to put the bonds in there for the carbon, and we're going to again zoom through it. You'll notice that this is lithium metal, so the electron has been given to the lithium ion, and that's where the electron is stored. Okay, so when you charge your battery, the lithium is in between the layers, and it's highly energetic. So you can see that there are, just like the metal oxide, there are layers, these honeycomb or sort of chicken wire layers of carbon. These are the graphene sheets, and then in between those, sandwiched between them, is the lithium. All right, you can take your glasses off now, because you need to be able to see this color change. So this here is a beautiful paper that came out last year showing this is graphite, and they're going to be charging the graphite. So this is the lithium coming in from this side. And I want you to notice what changes. So as the lithium goes into the graphite, it gives a little bit of its electron density to the graphite, turning it from a semi-metal to a metal. And that makes it turn this beautiful golden color, which I only realized very recently. And so every time you charge your battery, your cell phone at night, the graphite inside of it is turning golden, okay? But don't look inside of it, okay? You just have to take my word for it, okay? It'll be a bad time. As Akira showed us, it will not explode, but it will be the end of your battery. So when lithium goes into this material, into graphite, it forms this lovely golden color. This is called lithiated graphite. And another famous carbon scientist, Mildred Dresselhaus, in the 50s, studied this extensively as well. And what's interesting is the lithium gets sucked into it, okay? It's almost like it dissolves into it, gets sucked in, okay? If you've ever seen mercury put on a bit of aluminium, you'll know what that looks like. It kind of gets sucked into it and forms a mixture. Now, what happens when you connect turn on your phone and you start drawing electrons out of the battery? The lithium is dissolving into the electrolyte, because the lithium wants to dissolve, okay? It's like having a metal inside of some acidic solution. It wants to dissolve. And what happens when it dissolves is it becomes lithium plus. So where does the electron go? Goes into your device, runs all the way around your wires, and then goes onto the metal oxide side. So it's the lithium dissolving into the electrolyte that is giving you electrons to power your battery, okay? And you can actually make batteries just with salt solution and aluminium. And the aluminium dissolves into the salt solution, gives you electrons, and you can run like a little clock on it or a light. So it's literally as simple as that. Metals dissolving into some salty solution. Now it helps if you can shove them somewhere. So in the case of the metal oxide pulls the lithium over to the other side, and with the electron, it kind of is a safe place, is a good place for it to go. I like to call it the new gold rush. You put the lithium together, you put the graphite together, you make gold. Anyway, it's a little silly. So here is the sort of place I wanted to get you to. This beautiful kind of cobalt oxide, lovely blue color on one side. You've got the lithiated graphite, golden on the other, and this is the width of your hair. So It's all pretty wonderful. So hopefully that sort of inspired you to go out and get some more batteries and to perhaps, use these to power yourself. But there's, of course, the question of, well, how do we make these batteries without emissions? Because I said to you that, it's better to have an electric car versus a gasoline car, but gosh, they're expensive. Wouldn't it be great if they were cheaper? And one of the reasons it's so expensive is most of the materials used inside the battery are energy intensive. So nickel requires a lot of energy to make, and so there's a lot of focus at the moment on making those materials with renewable energy so that we can make electric vehicles cheaper, but also a lot less carbon intensive. So I'm going to talk about my science now. So let's just talk about the different lithium-ion battery chemistries. So all the different lithium-ion battery chemistries, there's different types of coloured pigments, metal oxides on this side, but all of them require graphite, okay? One of the challenges is that our supply of graphite is going to be a problem in the near future, and there's a supply shortage. Now, our focus is to synthesize graphite and to produce it so that we can enable this sort of shortfall to be filled. And that's a person for scale, by the way. So this is a huge ton-scale furnace. So what are the problems? Well, the first problem is that there are very few materials that form graphite. I mentioned to Marjorie that's able to turn coal into a tar that can form graphite. That's very unique. It's very hard to do, okay? There are only a few oil wells around the world that can produce the type of oil that forms graphite. And this is an unsolved problem in science, okay? Real puzzle. Keeps me up at night. Keeps many carbon scientists up at night. It takes days or hours at least a day to heat up to 3,000 degrees. Okay, that's the temperature required to make graphite. Very, very hot. And the amount of energy it takes per ton is actually similar to steel. And most of graphite production is from coal. So you can see how this is a problem. But remember, still about 50% better than if we were to just burn it. So the electric vehicle is still better, but couldn't we make it even more better is the goal. Okay, so let's talk about the science problem, because that is super exciting. So there's these molecules that when you heat them, they sort of form an aligned, cross-linked structure. And then when you heat them up to 2,500 degrees and 3,000, they form the beautiful layers of graphite. So these are those hexagonal sheets that I talked to you about. But unfortunately, and with much frustration, most materials like sugar form a char that, if you heat it up, forms this elaborate nanostructure that we call glassy carbon, and it is not able to be used in a lithium-ion battery. It can be used in a sodium-ion battery, but its capacity is not nearly as great. And there's actually a nice, so there is this question, what is the nanostructure of these disordered carbons? That's how I first came to this question, but it's related to the question of why is it so hard to make graphite? This problem was actually first highlighted by Dr. Rosalind Franklin, who you probably will most likely know for her X-ray diffraction pattern of DNA. So this is photograph 51 that she made of DNA, and this X here is diffracting off these layers here, giving you that diffraction pattern that allowed Watson and Crick to make the molecular model that showed that this is a double helix. Now, this photo was actually taken from Rosalind Franklin without her knowledge and given to Watson and Crick, which people aren't quite sure whether she knew about that. But before she did DNA, her first passion was carbon, and she looked at X-ray diffraction and she suggested that there are small bits of graphite that are misaligned inside of disordered carbon, but aligned in this graphite. And there's been a lot of work done on these defects. The defects actually stop the layers from coming together. They hold them apart, And that's actually a problem because the lithium, to get the lithium in there, you actually need to separate the layers. So the defects hold the layers at a very set distance and mean that the lithium cannot get in. That's why you have to heat to high temperatures. The layers come close together and then they're all free to move up and down. There's been a suggestion that there are some removable defects, but there are also some non-removable defects. And so we call these topological defects. Topology is a fairly nebulous term, but it just means that there's some shape or some sort of bonding motif that makes these hard to remove. And the first contribution that we made was understanding the structure of the disordered carbons. So these here are models of disordered carbons. This is more of an activated carbon structure. This is more of a glassy carbon structure on the right. And what we found is that these structures all possess, so I should mention, these were generated in the computer, a supercomputer, completely self-assembled. So we put the atoms in randomly and we let the computer anneal it, like you're cooking it, but in the computer. Okay, so the computer jiggled the atoms, bonds formed, bonds broke, and this self-assembled. And if you were to run it again, it would be different, but it would also sort of be the same disordered structure. And what we found is that there are screws, or these spiral defects in this structure, and that there are these sort of non-annealable defects here. We'll come back to those. Around this time, I went looking for these screw defects here inside of different materials, and it was hard in the disordered carbons to look at them. But at this time, Jason Fogg and Kate Putman had been doing X-ray diffraction, but also heating of graphite inside of a custom furnace that was developed. It's literally about the size of your thumb, and it can heat material up to 3,000 degrees in a second. It's very unique because, as I mentioned, the furnaces industrially used take a whole day. And even a lab-scale furnace usually takes at least 2 hours to heat up to 3,000 degrees. So this is very fast. Little tube, and we can heat up to 3,000 degrees. We usually take about 15 seconds, but we can go pretty fast. And what's unique is we can cool it down in a couple of seconds, which means we can freeze the process. And then we can do it again, and then we can do it again, and then we can do it again. And each time we cool it down, we can have a look at it, and we can see how it's changing. So how does the carbon turn into graphite? And this was the first time this has been done. So it's like stop motion footage of graphite in the act of forming. And this is one of my favorite instruments. This is an electron microscope. I like to say I have a dinner plate with atoms on it because electrons are boiled off a filament at the top, are transmitted through the sample. There are electromagnets that focus and form an image on a phosphor screen. The electrons get turned into light by a particular material, and then you look, like having dinner, at this plate, and there are atoms on it, which is really amazing. Great privilege to be able to use that instrument. And so we looked at graphite. So here is a crystallite of graphite, and those are the layers like this, but we can zoom in, enhance. So this is it enhanced. This is after a single pulse for 10 seconds, a 10-second pulse. And you can see that there's an alignment. Can you sort of see the dots as well, the little dots? Those are carbon atoms, like individual carbon atoms, which I just think is so cool. Anyway, I get really excited about seeing atoms, particularly carbon atoms. But you'll see I've highlighted this little area here because this got super exciting. As we cooked it for multiple pulses, we saw these sort of defects come together, and we saw these little zigzaggy ramp things between the layers. So you can see here that there are ramps between the layers. It turned out that our colleague, Dr. Irene Suarez Martinez, had studied this exact defect in her thesis a decade earlier. Does anybody have an idea what it is? What could produce those ramp structures? I'll give you a hint. DNA. Helix. Not a double helix, but a single helix. a helix of carbon atoms connecting the layers together. I actually have a 3D printed model of that here, just to help you out. Feel free to have a look at that. This was wonderful because as a scientist, when you come up with these ideas, it's very nice to actually see it and realize that you weren't just sort of making things up. So we wanted to use our virtual experiments, our simulations in the supercomputer, and we had an honours student, Gabriel Francas. So we put molecules or small fragments of graphene inside of a box, and we cooked it. We thought, okay, this is sort of like how graphitizing carbon forms. You get molecules that sort of align like a liquid crystal, and then that alignment means that when it is cooked, it can then form the graphite. So what we did is we did the same thing. We formed this aligned phase, and then we used molecular dynamic simulations. So this here is actually the bonds of the carbon atoms inside the simulation box. It's a bit confusing because it looks like this is going into nowhere, but this is actually connected to the other side of the box, okay? Which is a little bit of a trick that we use in order to make the carbon think it's in a solid, okay? So it's sort of trapped inside of a wrapped boundary. It's like a game of Pac-Man, okay? Go out one side, you get done by the ghost on the other. So that's how it works. So let's just see that go. Now, we were about 50-50 on this. Some of us thought it would form graphite, or at least some ordered structure. Some people just thought it would form something disordered. So we didn't take bets, but we were, we had a few guesses. And to our surprise, you can see the layers forming. Okay, but you can also see that there are screw defects in there as well. Not very easily, but if you 3D print the structure, it's much easier to see it. So I'll pass this around too. This is a 3D printed model of that simulation. And you'll actually be able to see on the top surface a screw defect coming down. Now, this is actually where the advanced visualizations that we're using here and that we worked with Dr. Andrea Rassel came together, because we were able to go to these immersive spaces. We were able to use a virtual reality headset in order to see these structures and to convince each other that there were actually screws in this model, okay? So this is where that sort of, that art is inspiring the science and making us do better science. So another way to look at this is we can look at the different rings and we can color them accordingly, according to cycle number. And we see, this is quite useful because it sort of sees the carbon, the graphene sheets like an actual mesh. And you can see a screw going up through that structure, okay? But this is something we couldn't do in the experiment. We could actually keep playing the video. We could keep the simulation going. How do they go away? And so that's what we did. We found that what happens is you form what's called a loop, a dislocation loop. So you have a screw of this right-handed screw, and then you have an edge, then you have a right-handed screw, then you have an edge, then you have a left-handed screw that kind of goes into the back there, and then you have an edge. And that forms a loop. Now I've actually, have I got one of those too? Yes. So this is what you're left with. You've got an edge here, then a screw, and then an edge, and then a screw. So feel free to have a look at that. There's 2 screws there. And so when we played the video, when we actually went through this, we found that you form a kink here, and then it runs along, the edge attacks, and then it frees the sheet above. And that keeps going until you're down to the 2 layers that I've 3D printed there. And then when they go, you've completely removed it, sort of unraveled. And this process we studied it in the computer, and we found that the speed at which these defects were removed are the same speed that we saw in the experiment. And so we're like, okay, I think we know what's going on. Okay, so what we did is we got all excited about screw dislocations and, and the mechanism of graphite formation. And we went to Imperial College London and we went to a conference, the Carbon Conference, and we presented our work and we said, look, this is how the graphite forms. Industry who was there, who makes graphite, looked at this plot here, which is the time that the layers go to the graphite spacing, and they said 200 seconds. That's really quick. That's really quick, And then this is only at 2,500 degrees. How fast does it form at 3,000 degrees? And I said, well, we can't measure it because it's less than 10 seconds. It's fast. What had happened is everyone had assumed that this process was first order, and they'd measured the kinetics on this side, and they found enormous barriers. But it actually turns out to be a second order process, which means that it speeds up as you get towards the critical point, which means that once you pass the critical point, it happens like that. And because the kinetics were incorrect, this was modeled as a first order process, but it's actually a second order process. Everyone was we know some companies knew that they didn't need to cook for so long, but some other companies, I think this was news for them. So graphite forms in seconds, not hours. Why does that matter? If you're pumping energy into a ton-scale furnace for 3 hours to keep it at 3,000 degrees for 3 hours, you're overdoing it. And this is we actually computed that the amount of energy that you need to form graphite is about 10 times less than how much is currently being used. And that's because of all the heat loss from the furnaces. So now that we know that graphite forms in this way, we're working now with companies and we've also developed our own company, to work out whether we can speed up this process. So can we now make new furnaces using renewable energy? So fast, rapid heating of graphite to make graphite more cheaply. So this is the conclusion slide, which is good. So I hope that at the end of today you can sort of put your phone on to charge by your bed and just think about those little lithium atoms, getting pulled over to the graphite through that electrolyte solution and then meeting up with the graphite and forming that beautiful gold color. And hopefully that little bit of wonder will inspire you to upgrade to that electric car, hopefully, or the electric moped, or in my case, an electric bike. Great form of transport. It makes biking so much fun, and it replaces my car. It's really awesome, I also just want to mention that beautiful link here with Rosalind Franklin. Not only did she do the double helix, but later on she worked on the tobacco mosaic virus, which is also a helical virus. It's just lovely to know that the problem that she first worked on in her PhD and first postdoc is also solved by, or partially solved by, the helical structure. So it's a nice bit of science there. In deep respect for C.V. Raman, what I have done is I've brought over another VR headset with an updated version that allows you to zoom through the structure of diamond. So you can actually see diamond, so I recommend that experience if you've never looked at diamond. And I also recommend building some of this diamond structure in the exhibition in response to Raman's excellent work in this area. And the last thing I just want to remind you of is to not think so much about your footprint, but think about how your handprint can leave a lasting legacy where carbon is not thrown up into the air, but is held onto and put into devices and into making the green energy transition a reality. So thank you very much.